So this video defines what we mean by a singularity in a complex valued function. We're going to use singularities to find our main asymptotic result in the follow-up video. So we say that a complex valued function, so x can take any complex value, is analytic at x naught if your function f can be expressed as a convergent infinite series centered at x naught. And that convergence has to hold for all values of x that are at least pretty close to x naught. So this definition means that analytic implies I can have a series expression for my function. And if I cannot do that at x naught, then f of x has a singularity. So let's see some examples. The functions e to the x, sine x, and any polynomial x to the 6th minus 3x plus 1, these functions have no singularities. There is no problem expressing any of these functions as a convergent infinite series centered at any value I'd like. The reason is none of these problems have any issues when I take derivatives, and if I could take derivatives of these functions anywhere, I could expand it as a series. How about the function? Let's call it g of x over x minus 2 times x minus 3 squared. So this function has problems at 2 and 3. I cannot expand g as a series centered at 2 because this function has a division by 0 at 2. That causes a real problem. So this has singularities at x equals 2 and 3. Let me do another example. You could also have a singularity when you have a 0 in a square root. So if I look at 4 minus x squared, this has singularities at x equals plus or minus 2. Those are when I have issues with a 0 in the square root. Now, most of the time for us in our examples, identifying singularities is actually pretty easy. So let's do another example. Let's say I have h of x, and let's say that's equal to 1 over 1 minus sine x. Well, this has singularities whenever I'm dividing by 0. And for us, that's most of the time going to be the problem. So if I'm dividing by 0, then I have a singularity. So this has singularities at any value of x that's equal to pi over 2, because that's when sine x is equal to 1, plus any integer multiple of 2 pi. So there are a lot of singularities for this function. Now, some singularities I can kind of get rid of by multiplying by the appropriate thing. So notice that if I look at this function g, then we see that 2 minus x, so I'm going to take this function g, and I'm going to multiply by 2 minus x. So 2 minus x times this g function, if I simplify, gives me negative x over x minus 3 squared. So I multiplied by the 2 minus x factor. It kind of canceled with this division by x minus 2, except giving me a negative 1. So when I did this operation, I removed the singularity at 2. So this no longer has a singularity at 2. So I multiplied by something to get rid of this problem at 2. This has no singularities at 2. Okay, one final example. What about this h? Can I multiply by something to remove the singularity at pi over 2? So if you look at this list of singularities, the one that's closest to 0 is pi over 2. Can I get rid of that one? Well, we see that if I look at the limit as x goes to pi over 2 of this function h of x times pi over 2 minus x. So what I'm trying to do here is look at this function h, recognize I have a singularity at pi over 2, and I'm trying to multiply by pi over 2 minus x to kind of get rid of the singularity like I did for this previous example. If I do this, then I have the limit as x goes to pi over 2. I think I'm going to get pi over 2 minus x divided by 1 minus sine x. This, if I take the limit as x goes to pi over 2, goes to a 0 over 0 form of a fraction. That allows me to employ L'Hopital's rule. So I have the limit as x goes to pi over 2. Using L'Hopital's rule, I get negative 1 over negative cosine x. And this still has an issue at pi over 2. If I try to take the limit as pi over 2, since cosine pi over 2 is 0, this still has a problem. Still a problem. So multiplying this function h by pi over 2 minus x doesn't remove the singularity at pi over 2. It's still an issue. However, if I take the limit as x goes to pi over 2 of pi over 2 minus x squared times h of x, maybe like I can multiply by a higher power of pi over 2 minus x and remove the singularity, such as, look at this example in G. If I want to remove the singularity at x at 3, I have to multiply by x minus 3 2 times to get rid of it. One time wouldn't be enough. So maybe I can multiply by 2 times this term, so x minus x pi over 2 minus x squared. So maybe I can get rid of the singularity by multiplying by 2 factors of pi over 2 minus x. Well, let's see what happens. So I get the limit as x goes to pi over 2. This time I have pi over 2 minus x squared over 1 minus sine x. Still I have a 0 over 0 issue, which I could resolve using L'Hopital's rule. So I now have the limit as x goes to pi over 2. I'm going to take the derivative. I think I get negative 2 times pi over 2 minus x divided by negative cosine x. And this time I again have a 0 over 0 issue when I take the limit as x goes to pi over 2. That allows me to do L'Hopital's rule one more time, and I have the limit as x goes to pi over 2. Now the top has derivative. Let's see here. The derivative would be 2, I believe. And the bottom has derivative sine x. Now, sine of x, as I take the limit as x goes to pi over 2, that's just 1. So I get limit 2. That tells me something interesting. That tells me that I can kind of get rid of the problem of division by 0 by multiplying by 2 factors of this term. Okay, so that's a very, very brief introduction to what we mean by a singularity. And we're going to use this in the next video to do something really interesting. Follow me along there.